Actually, in my previous two lectures, I gave you the definition of a binary operation and the definition of the group. And we tried to understand the group with some examples for say set of natural numbers, set of integers, set of complex numbers with two unit roots of unity, that is cube root of unity and fourth root of unity. We try to learn the definition of group, whether the given set along with the given operation is a group or not. We tried it. Now today I am trying to find the nth root of unity, the set with the elements u as nth root of unity is a group or not with the operation of multiplication. So let us define u is equal to 1 by n is equal to cos theta plus iota sin theta raised to the power 1 by n. This I can write cos 2 pi r plus iota sin 2 pi r raised to the power 1 by n. I can write this as cos 2 pi r upon n plus iota sin 2 pi r upon n, and is equal to e raised to the power iota 2 pi r upon n, where r is equal to 0, 1, 2, 3, 4. So this becomes, when we took r is equal to 0, it is 1, r is equal to 1, then it is e raised to the power 2 pi I upon n, and r is equal to 2, it is 4 pi I upon n, and so on, e raised to the power 2 pi n minus 1 upon n. This is set of roots of unity. This I can write 1 omega square omega raised to the power n minus 1, where omega is equal to e raised to the power 2 pi I upon n. Now, whether this is a group or not, we have to find the basic property. We have to prove that basic properties of group are followed or not. Say closure example, example closure property holds good as we told this binary operation, and the multiplication of this any two, multiplication of any two will again be a member of this family. So closure property holds. Associative property for complex numbers is already proved. Now for identity addition and identity and multiplication, a raised to the power n is equal to 1. Since any member of this raised to the power n will again be a 1, since they are root of unity. B raised to the power n is equal to 1. So a raised to the power n, b raised to the power n is equal to 1. That is a b raised to the power n. Any member, any two member a and b belongs to 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 the set. Say this set is k k. Then k a b belongs to k. Hence closure property holds good. For the sake of inverse, any two elements we can take omega. If omega is any member, then its inverse will be omega raised to the power n minus 1. This is omega n is equal to 1. So inverse of any element can be inverse, say omega r. Inverse of this can be defined as omega raised to the power n minus r. So their power will be equal to n and equal to 1. That is, multiplication of these two elements is again 1. That is identity. So inverse exists, identity exists, associative property holds good, closure property holds good. and multiplication of any two members, omega and omega square, say omega raised to power r, omega raised to power s, will be equal to omega raised to power r, and omega raised to power s will be equal to omega raised to power s and omega raised to power r. So abelian property also holds good, hence it is abelian group. Hence it means we can say that in general an nth root of unity is, along with the operation of multiplication, is a commutative group. This is another example of group. Similarly, for matrices, third is, say for matrices, if we take matrices, non-singular matrices, then the along with addition or multiplication, we can find that matrix multiplication and matrix addition will give us the properties of will follow the properties of group, and they are group. But in case of matrices, whether it is abelian or not, it depends upon the nature of the matrices which we are taking. Again, the fourth analyzed way, is addition and multiplication mode. Addition and multiplication mode. Addition and multiplication modulo. For this, we can take this set 0, 1, 2, 3, 4, 5 and addition modulo as 6. This is an algebraic structure. Say this is G and plus 6 as operation. Whether this will form a group, this structure will be a group or not, we can see by constructing the table as 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4 and 5. 0 and plus 0, 0, 0, 1, 2, 3, 4, 5. 1 plus 0, 0, 1 plus 1, 2, 1 plus 0, 1, 1 plus 2, 1 plus 1, 2, 1 plus 2, 3, 4, 5 and 6, 0. 2, 0, 2, 3, 4, 5, 0, 1. 3, 3, 4, 5, 0, 1, 2. 4, 4, 5, 0, 1, 2, 3. 5, 1, 5, 0, 5, 5, 1, 6 means 0, 1, 2, 3, 4. From the entries of table we can see that closure property holds good. Since this row matches with this row, means identity exists, left as well as right identity both are equal, hence identity 0 is the identity for this set. And inverse, since every row contains the identity element, so inverse exists for every element, left inverse as well as right inverse. Since 0 lies in every column, so we can say that left inverse as well as right inverse both exist. Hence we can say that this forms a group. This set forms a group. But if instead of this, if we take 1, 2, 3, the set as 1, 2, 3, 4, 5 and this operation as addition modulo 6, this will not be a group since the 0 does not belongs to the set G, say set G and plus 6. 0 does not belongs to the set, this set G, but in our table we can eliminate this, eliminate this, and 1 plus 1, 2, 1 plus 2, 3, 1 plus 3, 4, 1 plus 4, 5, and 1 plus 5, 0. This 0 does not belong to the set, therefore it is not a group. This will not form a group. Similarly, for multiplication modulus, if we take this as a set and operation is multiplication modulo, then we can construct again the table as mod 6, 1, 2, 3, 4, 5, 1, 2, 3, 4, and 5. So 1 into 1, 1, 1 into 2, 2, 1 into 3, 3, 1 into 4, 4, 1 into 5, 5, 2 into 1, 2, 2 into 2, 4, 2 into 3, 6, 6 means 0, 6 means 0, and 2 for 8 is 6, 2, and 2, 5, 10, 4. So here from this and these entries we can say this does not belong to the set G, hence this will not be a group. But if we take 1, 2, 3, 4 as a set and multiplication modulo 5, in this case we will see that multiplication modulo 5, 1, 2, 3 and 4, 1, 2, 3 and 4, 1, 1, 2, 3 and 4, 2, 4, 6, 1 and 8, 3, 3, 1, 3, 3, 6, 1, 9, 4 and 12, 2, 4, 1, 4, 4, 4, 8, 3, 12, 12, 2 and 16 means 1. Now here we see that all the entries belong to this set this. Means closure property holds good. Associative property in numbers, integers already exist. Since this row matches with this row, it means the left identity exists. This column matches with this column, so right identity exists, and left and right both are equal. So identity exists, and 1 is the identity for this set. And in each row there exists identity element. In each row there exists an identity element. It means, and similarly in each column there exists an identity element. So we can say identity exists, and inverse of each element also exists. Means inverse of 1 is 1, inverse of 2 is 3, inverse of 3 is 2, inverse of 4 is 4. So inverse of each element exists in this case. Also we can see that about leading diagonal, this is symmetric, this is symmetric, so this is an abelian group. So in these two cases, from these two cases we can understood that if this is a prime number, in general we can generalize these two from these two. If this is a prime number, then this will form a group, otherwise will not form a group. So we can prove it by in general that if we are given a set 1, 2 and m minus 1 and multiplication modulo n, this will be a group if m is prime. We can prove it easily by using the basic definitions of the numbers. We can prove that this will be a group. So from these examples we can say that whether the given structure forms a group or not, we can analyze the things very well. Thank you.